most respected learned professors, research scholars and students. Good morning to all. So before my speech, I would like to thank the management of ARULMIGU PALANIANDAVAR College of Arts and Culture, and also I thank the HOD of Chemistry, the PALANIANDAVAR Arts and Culture College, and my special thanks Dr. Viswadhari, Assistant Professor of Chemistry. So this is for a wonderful opportunity to deliver my talk. So thank you once again. So let's go to our topic. So today our content of this webinar, the introduction on electromagnetic radiation, properties of waves, UV visible spectroscopy, IR spectroscopy, Raman spectroscopy, NMR spectroscopy. First of all, we must know that what is EMR, electromagnetic radiation. So this is for 1864, the Maxwell suggested that the alternative current of high frequency is capable of the radiating energy in the form of waves. This waves motion consists of electric and magnetic field. So this way, electric and magnetic field, so which is directed perpendicular to each other. The velocity of radiation is almost equal to that light. So this is called as a electromagnetic radiation. You see the image here, right? So what is the source of the electromagnetic radiation? So the source is sun is the source of the radiation. So every second, every minute, the sun will give the radiation to every particles. So this is the source of the electromagnetic radiation is sun. So if the matter, the interaction of the electromagnetic waves with the matter, so there are the two possibilities. One is absorption, another one is emission. If the particles or matters are absorbed some energy for EMR, electromagnetic radiation, they are giving some value, they are giving the some signals, that is called as a spectroscopy. So units, here there are the two units as important. One is the wavelength lambda, distance between two nearest crust and thrust, crust or thrust. So this is for crust and thrust. So this is distance between the two nearest crust. This is called as a wavelength lambda. And then what is the frequency? The frequency is the number of wave cycle in the given time for the measured in hertz. So this is for the total cycle is a frequency. Another, so this is for the electromagnetic spectrum. So electromagnetic spectrum, they have the many radiation, gamma radiation, X-rays, UV visible, IR, microwave and radio frequency. Here the visible region we can see only the violet, blue, green, yellow, orange, red. So other than radiation we cannot see because of only for we can see the visible region only. So another region, so some other rest of the region we cannot see because of that is not our region. So I can detect only for the visible region. So this is a region of the electromagnetic spectrum. The region, the wavelength of Armstrong, the wavelength of centimeter, frequency, hertz and energy. So here the some image for visible region this is for the radio frequency 10 to the inverse, and this is for the IR region. Microwave region, this is 10 to the power minus 1. 10 to IR region is 10 to the power minus 3 to 10 to the power of minus 5. So gamma rays is 10 to the power of minus 9 to 10 to the power of minus 11. So there is a total of electromagnetic wave spectrum or regions. So another, what is interaction with the EMR? If the atoms or molecules absorb some energy or EMR, so what will be happen? Our atoms or molecules absorbed with the EMR radiation, they are giving the some signals. So regions of the electromagnetic spectrum, region of and the spectrum. The radio frequency is NMR spectroscopy, microwave spectroscopy, ESR, rotational spectroscopy. The IR radiation is FTIR spectroscopy, electronic radiation, UV visible spectroscopy, inner cell electronics, UV visible spectroscopy. Near nuclear reaction is gamma rays. So this is the there are the what is the region, what is the spectra. So another, what is spectroscopy? Spectroscopy is the study of the interaction of electromagnetic radiation with matters. Already I told you. So spectroscopy, there are the two types. One is atomic spectroscopy, molecular spectroscopy. What is atomic spectroscopy? The EMR interact with the atom, and then molecular interact with the EMR. So this is the difference. So electromagnetic radiation interaction with the atom, the electromagnetic radiation interaction with the molecule. So this is for the, already we know that the ions combined with the atom, atoms combined with the molecules, molecule combined with the compounds. So this is for the fundamental. The types of molecular energy, there are the 4 types of energy is there: translation energy, rotational energy, visible vibrational energy, electronic energy. So this is for the molecules, liquids or gas phase. In case of processes of these type of energy are in our molecules, atoms or molecules. So E total equal to E greater than transitional, E rotational greater than E vibrational greater than E electronic level. The types of molecular spectroscopy: UV visible spectroscopy, IR spectroscopy, Raman spectroscopy, NMR spectroscopy, ESR spectroscopy. So this is the types of the molecular spectroscopy we can discuss here. The first of all, we are going to discuss about the UV visible spectroscopy. What is UV visible spectroscopy? Basically, this spectroscopy arrays the excitation of electrons in the molecule from bonding orbital to anti-bonding orbital by the absorption of the radiation energy. Here the radiation means electronic energy. Here sometime UV spectroscopy we called as a electronic spectroscopy. Here the involved of radiation range from the 100 to 400 nanometer, and then visible region is 400 to 800 nanometer region. So selection rule. So spin selection rule is delta S is equal to 0. The allowed transition singlet or triplet or triplet. The forbidden radiation, the singlet, triplet or triplet, singlet. So here the ground state of singlet, the excited state of singlet. So triplet or singlet or triplet or singlet is forbidden transition. So singlet or triplet are allowed transition. So this is a selection rule for the UV visible spectrum. UV spectrum. So UV spectrum, the plot of wavelength of absorption versus to intensity of absorption of transmittance. The main, it is a first wavelength of peak maximum lambda max, and then second intensity of the absorption peak is E max. So we calculate two values for lambda max and E max. So types of electronic excitation. Here the energy in the form of light. If the molecule vibrate in ground state, when the atoms or molecules receiving the UV radiation, suddenly the molecule is ground state to excited state. Molecule goes to electron goes to ground state to excited state. I mean bonding orbital to anti-bonding orbital. Here there are the sigma star and sigma pi star and n pi star. Here the sigma bonding and bi bonding and non bonding. So another one is anti-bonding. Sigma to sigma star is carbon single bond, there are the strong bond. Another one is a sigma to pi star, carbon double bond, less than of sigma to sigma star. Another one is n bonding. N bonding is in case of electron withdrawal groups for OH, NH, these are the non bonding groups. These interact with the electronic excitation. So this is for the electronic excitation, pi star, n pi star and sigma to sigma star. So what is visible region? So above 400 to 800 nanometer is visible region. So when the light is passed through the prism, so the dispersion angles, there are the many colors is there. So in case of violet, our compound is synthesized, some other colors is appear. The violet, indigo, blue, green, yellow, orange, red. So there are appear in the 400 to 800 nanometer. So we can easily find out our compound is color. So this is this spectra is will useful to what color is observed in our compound. So this is for the UV visible instruments. We can easily find out this using these instruments. Another UV spectrum, UV visible spectrum. Here we have prepared one compound For there are the two regions already told you. 200 to 400 is UV visible region, 400 to 600 is visible UV region. 200 to 400 UV region, 400 to 800 is a visible region. Here our compound having the color, so that will be it is observed in visible region. Another pi star and n pi star absorbent appeared in 200 to 400 nanometer. So this is the UV spectrum. Another, the application of UV visible spectrum, the study of the functional group, the detection of functional group are chromophores, and the identification of functional groups are chromophores, determination of cis-trans isomerism, geometrical isomerism, nature of double bonds, study of the conjugation. So this is for the UV visible spectrum applications. Another, the applications of UV visible spectroscopy, we can calculate the lambda max, E max and solvent chromophoric group. In case of methanol is 177 lambda max and E max is 200. Here the solvent is hexane and chromophore is non-chromophore. 1,3 dibutane is lambda max is 217 and 21,000 E max. So his solvent is hexane and then simple conjugated double bond. So benzene is 204 and 7,900 for E max, and solvent is hexane, the aromatic system. So we can find out easily the lambda max and E max are chromophoric groups. You can easily find out the UV visible spectroscopy based on the Woodward rule. Another spectrum is FTIR spectroscopy. So what is a FTIR spectroscopy? Here the theory, the bonding is every bond in a molecule vibrates and produces a change in dipole moment. Change in dipole moment. Dipole means delta plus and delta minus. This change in dipole moment provides a mechanism for the absorption of radiation. Consequently, every bond is molecule has the observed band or peak in the IR spectrum. Intensity of the IR band or peak depending upon the magnitude of change in dipole moment. So position of the IR spectra specified into wave number mu, which is measured by the reciprocal of the centimeter inverse. So this is theory. So first we can find out what is FTIR spectroscopy. The spectrum is very useful to find out the functional group or fingerprint region. So change in dipole moment, that is very important. The magnitude of change in dipole moment, we can easily find out some other compound. So FTIR spectroscopy, the IR radiation in the part of electromagnetic spectrum between the visible or microwave region. Here the using of visible or microwave region. There are the three regions is possible. Here the far IR or near IR spectrum. Far IR is 700 to 200 centimeter inverse and IR is 400 to 650 centimeter inverse. The near IR region is 14,000 to 400 centimeter inverse. So this is for the fundamental. So IR spectra is detect only for the 4,000 to 650 centimeter to 4,000 centimeter IR region. So we can easily find out if we collect some compound using the IR spectroscopy, we will get this spectrum. Okay, this is for the spectrum, the wave number and absorbent. There are the two region is there. So our region is 652 and 4000 centimeter inverse. It is a IR spectroscopy region. Here the below 1500 it is a fingerprint region. So if we get some bending groups means scissoring, wagging, rocking, twisting, some other the fingerprint, it's a rare values will be observed here. That's carbon single bond bending groups, carbon single bond nitrogen, carbon single bond. This is a fingerprint region is a below 1500. Another is above 1500 is functional group region. So this functional group region, there are divided in three types. One is the double bond region, triple bond region, single bond stretching vibration. Here the double bond means carbon double bond, carbon double bond O, and carbon the keto groups, aldehyde groups, some other groups are appeared. So there are the double bond is appeared in range of 1500 to 2000. Another is triple bond is appeared in, for example, nitrile groups, 2000 to 2500 region. Another above 2500 to 4000 region, we can single bond stretching. Here the main important aliphatic carbon and aromatic carbon stretching at vibration is appeared in nearly 2500 to 3000, and then it is OH and NH stretching vibration is appeared in NH touching vibration is 3300 to 3350 and OH is above the 3500 centimeters. So this is the overall view in this region. We can, if we synthesize a new compound, we take the FTIR spectroscopy, we can easily find out the functional group, what type of functional group is we present in this molecule. So always we are finding some finger groomed region also. Okay, so this is for IR absorptions of common functional group. The alkane is CH, range for absorption location 2850 to 2975, the medium to strong. Algal is 3400 to 3700, strong band. And then alkane carbon-carbon double bond, it is range of 1640 to 1680, weak medium. And then the 3020 to 3010 is medium. And then alkyne is carbon-carbon triple bond, it is 2100 to 2250, medium, and 3300 is strong medium. The nitrile means cyanide groups appear in 2200 to 2250, so medium. And aromatic is 1650 to 2000 is a weak band. This amine, in case of NH amine groups, NH touching vibration is appeared in 3300 to 3350, medium. Another, it is a strong carbonyl, aldehyde, ketone, ester or acids. These group appear in 1720 to 1725 regions. So strong absorbance will be appear. So these are IR absorption of the common functional group. So this is for the FTIR spectroscopy instrument. We can standard KBR reference compound have the KBR potassium bromide. We can take this our compound. So like this. Another Raman spectroscopy. So what is Raman spectroscopy? Basically, Raman spectroscopy is commonly used to chemistry provide the fingerprint by which is a molecule can be identified. The relies on inelastic scattering or Raman scattering of monochromatic light, usually from the laser in the visible or near infrared or near ultraviolet. So there are the difference between the IR spectroscopy and Raman spectroscopy. The symmetrical stretching is no change in dipole moment. There are the IR is inactive, and then the change in polarizability, therefore the Raman active. And then asymmetric stretching is a change in dipole moment, IR active, and no change in polarizability, the Raman is inactive. In plane bending, the IR is active, polarizability is no change in polarizability, the Raman is inactive. So out plane bending is change in dipole moment, there is no any answer in for Raman spectroscopy. So in case of Raman spectroscopy, it is a vibrational states and virtual states. There are the two states. We collect the Stokes scatterings and Rayleigh scattering and anti-Stokes scatterings. So here they see you molecule having observed in Raman's rays for 1 to 10 to the power minus 7 proton is scattering of inelastically. So excitation of Raman scattering, excitation and scattered. So virtual states, so V is equal to 0 to V is equal to 1. And there are the three rotational, vibrational, and electronical Raman spectroscopy. We collect the Raman is 1 counts to 1 laser to 1007 counts. We can easily find out this spectrum. So what is the application of the Raman spectroscopy? Structural chemistry, solid state chemistry, analytical chemistry, applied mathematical analysis, process of control, microscopic imaging, environmental monitoring, the biomedicals. There are the many applications. Presently we are sending the some other space research also. We can use this spectroscopy. As another next important one important spectroscopy is nuclear magnetic resonance, NMR. So this is for this is for the instrument of the NMR spectroscopy. So this spectrum is this spectroscopy is used to find out how many carbon present in your molecule and how many hydrogen present in your compound. We can easily find out the structure in the solution states. So this is for the NMR. The interaction between the nuclei and the radio frequency of radiation is called as a nuclear magnetic resonance. So these are nuclei of certain atoms or molecule consist to the spin. So these options of external magnetic field, the spin states of the nuclei are degenerate, the possessed to equal the energy level. In the presence of the external magnetic field, degeneracy is removed and separate the energies level are possible. This is for the fundamental concept. What is the selection rule? In case of odd, mass number is odd, atomic number is even, NMR is active, and then mass number is odd, atomic number is odd. So that is NMR, nuclear spin is I is equal to of 3 by 2, 5 by 2. So NMR is active. Even is NMR inactive, even odd is NMR inactive. So this is for the selection rule. The instrumentation of NMR spectroscopy. So here you see this magnet. So if the magnet is increasing for 300, 400, 500, 600, 900 megahertz, the compound resolution will be increased. So you take this compound in this magnetic region, magnetic field, and then additionally we can give the radio frequency transmitter. So this is for detection, this is for observation. We can take this printer. So this is for the instrumentation. So here the sample preparation. If we prepare some sample for using the solvent, for example, without hydrogen the solvent, for example CdCl3 and DMSO. So these type of solvent is options of hydrogen. We can use this solvent. So suddenly the spinning is there. So magnet is north and south. So this is for in case of our molecule having the spinning. The proton which is the right amount to energy can be observed. Case of the spinning proton is flip. For example, alpha state to beta state. The value for energy for h nu is equal to delta E. I means B naught is give the plus of alpha state and minus of is beta state. So this is for the spin energy states. Alpha state to excited to beta state. So suddenly the spin relaxation and spin lattice will be there. So we can collect the signal easily. So this is the principles of the NMR. So if the molecule, if the nuclei have no external magnetic field, spin of the nuclei and its generation of magnetic field, without an external magnetic field, the nuclear spin or the random in direction. But the external magnetic field B naught is present, the nuclei aligned themselves to in the aligned with the field of the external magnetic field. In case of upside or downside, so this is for the aligned, this is for the opposing. So there are with external magnetic field is there. Another, so we can represent the magnetic movement of our nuclei using this single arrow. So this is for energy. Okay, we can give the external magnetic energy. So suddenly we can meet this here. This is for shielding, and then this is for the deshielding. Aligned and opposed these ways. So case of spin is off is B naught external magnetic field given to nucleus with spin lower energy generation to magnetic field, the direction of the external magnetic field. So energy gap of the corresponding to radio frequency, and then it is a nuclear with the spin higher energy generate magnetic field opposed to direct of external magnetic field. So this is for the nucleic are electrically charged and may have to spin the cause with the behave like the magnetic. So another is type of NMR spectroscopy, the proton NMR spectroscopy, C13 NMR spectroscopy, P31 and silicon 29 NMR spectroscopy. Another Fourier transfer NMR is solid state NMR, etc. We can easily this type of molecule we can find out this solid state one. What is chemical shift? The shielding and deshielding we can discuss there. The field record to hydrogen to resonance, the verify the slight with the chemical environment of the hydrogen. So record the difference between the hydrogen of the sample and it is a TMS or tetramethylsilane is standard reference. Why we can use the TMS? It is a TMS chemically environmentally same. It is we get this single peak. So this what is chemical shift? Delta is observed the position of the peak heads and operating the frequency in the instrument. Delta in 10 to the power minus 6. So this is for the chemical shift. There are chemical shift values upfield and downfield. So upfield is a shielding and downfield the deshielding field. So upfield is 0 to 5 and above the 5 to 10 is downfield. So in case of alkane or some other halogen groups present in the upfield, and also it is downfield is go to keto groups, some other aromatic groups appeared in downfield. Another chemical shift. So this is for the region. The proton number is observed in 0 to 10 ppm parts per million, and then it is carbon 13 NMR spectroscopy is 0 to 200 ppm. So ppm here is the parts per million. So why it's a carbon having the 0 to 10? Because of the proton is 100% natural abundance. So you take minimum 52 second in spectrum scanning time. So suddenly we collect the how many proton present in your molecule. If the proton is appeared in 0 to 1, it is alkane, and 1 to 2 is alkyne, and then 2 to 3 are 2 to 3 to 4 is a halogen group in case present. For methoxy group, some other halogen group is present. Appeared in halogen protons is appeared in 3 to 4, and 5 to 6 is appeared in this carbon-carbon double bond in case of any carbon-carbon double bond having the proton, that is appeared in 6 to 5. And then 7 to 8 is aromatic CH protons appeared in this region. Above the 9 to 10 is appeared in aldehyde or acid proton is appeared in this region. Delta S equal to downfield is deshielding region. And the same things, it is a carbon 13 is 0 to 200 ppm, the parts per million. It's appeared in 0 to 20 or 0 to 30 is alkane carbon is appeared, and then 30 to 50 or 60 is halogen carbon is appeared, and is another way the 100 to 150 is appeared in carbon-carbon triple bond or aromatic carbon appeared in the region. Aromatic carbon is appeared in this region. Above the 150 to 200 is aldehyde, ketone, acids, carbon is appeared in this region. So this is the chemical shift of value. So here you see some one example for the ethanol spectrum. Ethanol formula is CH3, CH2, OH. There are the three environmental is possible. Here the n+1 rule is possible. One is A is neighboring, we choose the neighboring group, and CH2 is neighboring group. Here the electromagnetic group is that this is not coupled with the neighbor. So then A, B, C here. So here the concept of CH3 gave the triplet because of CH3 neighbor group CH2. So n+1 is a triplet is appear, and then CH2's neighbor group is 3 and appeared in quadret groups, and OH is appeared in singlet because of OH group is not coupled with neighbor because of electromagnetic group is present. So already we know that the TM is tetramethylsilane is typically magnetically equivalent, so it is appeared in 0. So this is for standard. So here the using the Pascal rule for singlet is 1, doublet, triplet, quadret, quintet, sextet, subset. There are the above the quadret we are talking about the multiplets. So this is for the ethanol spectrum. Another one spectrum is proton number spectrum, ethyl benzene. Here see the methyl group is appeared in 1 to 2 region, and then it is a CH2 group is appeared in 2 to 3, and then aromatic group is appeared in 6 to 7 region. So this is for the proton number spectroscopy of ethyl benzene. So another one important application for the medicinal field, MRI scan is also it is advantages of the NMR spectroscopy. We can easily, in case of insured in our head, we can easily find out the image. So using this advanced spectrum for MRI scan. So this is fundamental concept of the NMR spectroscopy. In our research, based on this spectroscopy, we can using this spectroscopy we can easily find out the some unknown compound. So this is for my research for design, synthesis, characterization, confirmation, biological investigation of NSI piperidine 4,1. So I prepare the 3-methyl butanol and to paramethoxybenzaldehyde. I prepare the piperidine 4,1, and using the derivative of the more than 4 compounds for phenyl carbamyl, acetyl or chloroacetyl morphine compound. So first we can easily find out this parent compound having that there are the 2 functional group is there. It is a keto group is appeared in 1700 centimeter minus 1 and stretching vibration, and then 3300 stretching vibration is appeared in NH stretching vibration. So I can easily find out this my parent is having the 2 functional group, and then aromatic region is appeared in this region. So this is for fingerprint region. So another one is derivative. So phenyl carbon compound. So I am substituted here the NH. NH is disappear, and in this present new NH is appeared. So that is a new NH is 3301 centimeter minus 1, and then it is for 1600 the 1700 additional carbonyl stretching vibrations appeared in 2 way. This is for we can easily find out there are the 2 carbonyl group, and NH group is easily find out this derivative compound. So another one is mass spectroscopy. So I can find out the my molecular weight is m by z is 458. So and then so you can easily find out the molecular spectroscopy. Another one is see the this is for the derivative compound of phenyl carbonyl derivative compound of proton NMR spectroscopy. We can easily find out the doublet of doublet, triplet of doublet, some other values for the 0 to 9. So I can find out the compound. So like this. So this is for the 2D NMR spectroscopy, HH COSI, the hydrogen correlation, which hydrogen is correlated with another carbon. So I can easily find out this molecule in using this COSI spectra. So this is for the C13 NMR spectra. So how many carbon present in my compound? So I can easily find out this region. For here the 2 methyl groups is there, another one is C5C2, some other methoxy group is there, range of 40 to 6 ppm, and then is aromatic region is 122 and 140, and then another 160 another one carbon double bond, and then keto group is C4 is appeared in more than 200. So I can easily find out my compound. So this is for depth NMR spectroscopy. In case of hard carbon, even carbon is there, we can easily find out the diagonal for up and down. So I have only for CH2 group is C5. So this signal for identified this group. Another group is appear in upside. So this is for the add carbon. So this is for CH COSI, carbon and hydrogen correlation spectroscopy. So in case of we synthesized organic compound, definitely carbon and hydrogen is there. So the carbon, which carbon is correlated with which hydrogen, and ECD you can easily find out this using this spectroscopy. So this is some other values for proton NMR and C13 NMR spectra for chemical shift values, and then this is for the coupling constant of the values. We can easily calculate with proton and C13 NMR spectroscopy. And then it is C13 NMR chemical shift values or DC shielding or de-shielding, we can easily find out this spectrum. So another way is solid state chemistry. In case of we are doing in the solid state chemistry research, so same things I prepare, I grow this on compound for the new class of phenol material. So this is also, it is isopropyl 1541. So you see these crystals, we collect the big crystals. So I take this UV visible spectroscopy. I will here the 200 to 400 region is UV region. I got only 5 pi star and pi star transition only. So our compound is, there is no any color. So here the 400 to 800 there is no any absorption in the entire the region. So I can conclude my compound is colorless and is very transparency using this UV visible spectroscopy. Then it is a Fourier transfer FTIR spectroscopy. I can easily find out the NS touching vibration and keto vibration, and then some other aromatic group is easily find out. Then another way is proton NMR spectroscopy, and then it is so in case we are in research or we are in project, we are involved in some other we synthesize some other compound, some other new compound. You can take this UV visible NMR some other spectroscopy. You can easily find out what are the present in your molecule, what are the function group is present, what are the bonding is there. So finally you find out the what type of compound you are collected. So this is for the application in chemistry and physics and medical as well as the pharmaceutical field. So let's see. Another one is a conclusion. The spectroscopy is the physical and analytical chemistry because of atom molecule have the unique spectra. As a result of this spectra can be used to detect, identify the quantified information about the atoms or molecules. Spectroscopy is also used to astronomy and the remote sensing and as well as the space research. So this is the reason it is spectroscopy is presently very rich development in nowadays. So this is my conclusion. Thank you. So I thank every participant, and also it is once again I thank to ARULMIGU PALANIANDAVAR College management, principal and Visudharni madam. Thank you madam. Thank you.